so welcome everyone for this new SIPTA seminar of February. Okay, today I will be chairing the whole seminar because I'm the one that has invited Rafael mainly. So Rafael is currently associate professor in Milano Bicocca, and his main interest is in artificial intelligence, I would say, and mostly logical modeling and deriving new logical frameworks, particularly extending classical logic to handle various problems. So it can be non-monotonicity, it can be taking account of the time, which is one of the things we will talk about. And it's also ought to include aspect of uncertainty into this kind of logics. And this is precisely what you will talk about. So we can mix time and uncertainty into logical reasoning, and a tale of superpositions or a tale of two logics, if you want. So this is his talk. So Rafael has many things I could tell about, but his responsibilities in Big AI conference. He regularly published in KR, in HKI. So he's and in fact, I met him at XCARU, where he gave a talk about the same topic, and I thought, okay, this talk could be quite interesting to emphasize probabilistic people. So that's where I invited Rafael to give a talk. So I am myself impatient to listen to him again, because this was a very nice talk in XCARU. So Rafael, without further ado, I give you the floor.
Okay, so yes, so again, thank you again for the very nice introduction. And yes, as you have heard, so I'm going to speak about uncertainty, so probabilities, and temporal reasoning, temporal logic, and how to make these two things together and make them work. And we will get to the part on imprecise probabilities, so I hope you will get something interesting out of it. But before starting with the imprecise probabilities, I just want to give you a small I want to put you in the context of why we were working on this, so me and some of my colleagues that are in Bolzano and also in Germany. All this started with an idea that we are dealing with business processes. So this comes from a totally different area, or let's say a sub-area of AI, but that is not so much considered as a part of AI in general, but it's business process modeling. And the idea is that, so imagine you have your own business, like, I don't know, an online store, some kind of business that is trying to, there is a flow of information that is, of course, time dependent. And we are trying to represent how these processes work formally so that we can reason about them and then get some conclusions out of them. So the idea is very simple. So why do we want to do this? Well, first, because we want to understand the golden standard, right? So if I have my business that is running for a long time, maybe I want to understand how it works, how it runs, so that I can predict, again, things that will happen in the future. That's one possibility. Another thing is that maybe we want to make sure that some things will not happen in our business, right? So we want to make sure that our processes are robust enough to avoid some unwanted behavior. Okay, so a simple example that doesn't come from business processing, but from temporal processing is the usual traffic light example, right? So if we are describing the traffic lights in a corner, we want to avoid that both sides in the same corner have the green light at the same time, right? Or we want to avoid that nobody is able to pass. So those are two kinds of unwanted behavior that we want to make sure that never happen in a traffic light. Well, in a business process, there would be other more complex examples that we will see in a second that we want to avoid. Another thing is we might want to be sure to guarantee a certain service, right? So now returning to business processes, for example, we might want to guarantee that if I have my online store and a customer orders something and pays for it, then that I will be able to, that this customer will receive the package that they bought, right? So I'm guaranteeing the service. So I want to make sure that after an order has been paid, it will be delivered to the customer after some time, but also hopefully in a short amount of time. But this is a different kind. And now, so the point is, how do we represent these business processes? Well, in general, the idea is to use a declarative language. And the way it works is that we describe some kinds of constraints on how the process evolves. So if I have if I have observed certain behavior so far, I have to restrict what is the future behavior of the process. Okay, so that's the basic idea of formal representation of business processes. Okay, now within this big area of business process, there is one language that we care about. So this was developed by some of my colleagues. So I entered this work later after this was already described. But this is a very simple specification language. I will show you an example in a second. And as I mentioned in the previous slide, the idea is that it will just restrict the potential relationship between actions, right? So we are again dealing with business processes. So everything that we do in the process is called an action. And what we are doing with the declare specification is to restrict what actions can appear together and which can appear after which others, right? So the temporal relationships between the different actions. So again, for example, if a customer has already paid an order, right? Then they cannot go and remove something from their cart if we are in an online store, for example. So we will restrict the kind of behavior that they can do, okay? And the goal of this specification language is to give it to somebody that can be, so to users that can read them easily. So it was developed in a way that it has to be a representation that is graphical and easy to see. So we will see in a second. And to make it simple, this language, declare, it only uses very simple constraints formally. Okay, so here is an example of a declare process description. Okay, so I don't expect that you immediately understand everything that is here, but you can see that we have different kinds of arrows that connect the different items in here. So we have certain restrictions, like say, for example, that canceling an order and asking for a refund, okay, they cannot coexist, right? So if I get a refund, I cannot cancel the order. If I cancel the order, I cannot get the refund at the same time, okay? So these would be things. Then, for example, here we have that if I ship the order, then afterwards it cannot be canceled anymore, okay? So this is also a restriction, okay? And then we have the different arrows. So these are, again, I don't expect you to understand all of this immediately, but as you can see, the general description is graphical and very simple, okay? But the main point, of course, is that this has to have a formal meaning, right? So this specification has to have a formal meaning that we can then manipulate and get conclusions out of it, which is the goal of business process modeling, of course, right? So some of the restrictions that we can see here or examples that we might want to describe in a business process. So again, returning to this example of an online store, for example, we might want to say that we should only ship an order if it has already been paid, right? So as long as the customer has not paid, I will not ship anything, right? Even if they have already closed the cart, etc., they are not shipped until we get the payment, okay? Which makes sense for an online store, right? Now, this is good for us, right, as a business, but we should also see the side of the customer, right? So this is the other example that I had mentioned. So if the customer has already paid, then we must make sure that this order is delivered to the customer, okay, at some point in the future, hopefully not too far away in the future, but it should be delivered at some point, okay? Now, another restriction that we might want to say in this kind of setting is that if a customer wants to get a refund of their order, okay, well, they must first return their product, okay? So if they say, no, this is defective or whatever, I want a reimbursement, well, the customer should first return the product, and then only after that was been returned, we will reimburse it to them. Okay? Again, this also makes sense for us. Or I cannot have, so another, just this is like a sanity constraint, right? I cannot have an order that is at the same time open, so where they can still add items to the cart, for example, and closed where they have finished ordering their package. Okay, and well, we can stay here for hours and hours just thinking of constraints of an online store. Just to give a last example is that if a customer has not added anything to the cart, then they shouldn't be able to pay, right? Because they don't have anything to pay about, so I shouldn't even give them the option to pay. So it should be disallowed. Okay, and then there are many other restrictions. Now, of course, in a real example of an online store, we will have thousands and thousands of these constraints describing the whole process, right? This is the goal. Okay, now, coming back to the logic, right? So this declare language is very nice, it's graphical, it's very easy to read, and we can show this also to the, to the managers, to the owners of a business to show their process. But as I mentioned, so we need a formal specification for this language. And in the background, okay, these declare constraints are just a different syntax for what is linear temporal logic. Okay, so here I wrote it in the abbreviated form. So we have a temporal formalism, a temporal logic to handle formally all these restrictions. Okay, so just to describe very briefly what this LTLF means. So for those of you that know a bit of temporal logics, so LTL is the classical linear temporal logic, which in its classical form, which is used for verification of processes, usually thinks of infinite time. Okay, so this small f afterwards states that we only deal with finite traces. So we are dealing with linear temporal logic over finite time. Why? Because contrary to verification of, let's say, software packages, we assume that a business process will always terminate. So we don't know how short or how long it will be, but it stops at some point, right? And then we start a new process, but we have each process is finite. Okay, so that's why we have LTLF. Okay, now let's get a bit more technical about what this LTLF means. Well, here I just have the syntax, the syntactic rule for describing the formulas, but I will try to say it by words. So the LTLF formulas are all kinds of propositional formulas. So if we can express everything that we can express in propositional logic. So we have propositional variables, negations, and conjunctions. And since we have these two, of course, we have disjunctions and implications and everything that we can do with propositional logic. Okay, but then, of course, we need some operators that speak about time. Okay, so it allows us to have these two new operators. So this circle here is read next. So it's stating that in the next point in time, the formula phi will be true, right? So saying that in the next point in time, I will pay, for example. And then we have this other formula that is called the until, that says that the first formula phi will be true until we observe the second formula. Okay, so for example, an order is open until the customer pays it, for example. And so the moment they pay it, then it becomes closed. But before, at every point in time, it will be considered as an open order. That could be a simple example. Okay. So as I mentioned before, so LTLF is syntactically, for those of you that know LTL over infinite traces, is syntactically looks exactly the same, right? So we have, again, the next operator and the until operator and all propositional formulas. But the only difference is that we deal with finite time. Okay, so each process, we know that it will terminate at some point. Okay. This looks like so at first sight looks like a trivial modification of LTL, but it has some important consequences. So there are things that in LTL are equivalent, but in LTLF are not equivalent because of the limitation of finite time. But these are very technical details that I would not go into here. But so just to give you a small example, okay, in LTLF, okay, the formula not next f. So what we are saying is not true that in the next point in time phi holds. Okay, so it's not true that in the next point in time I pay. Okay, for example, is not equivalent to the formula in the next point in time I will not pay. Okay, why is it not equivalent? Because the formula on the left has two options. So I have the option that I have a next point in time, and at that point in time, I do not pay, which it would be what this one is expressing. But it could also happen that I just finish my process now. So since my process finished now, there is no next point in time. And so it's definitely true that that in the next point in time, I will not pay because there is no next point in time. That is not true that in the next point in time, I will pay. Okay, in LTL over infinite time, since there is always a next point in time, these two formulas are equivalent. Okay, so this is again a very technical thing, but just for those of you that know LTL to showcase the difference between the two languages. Okay, now I will use for this talk, I will try to keep it as not as limit the technicalities as much as possible, but we have the usual abbreviations that LTL has again. So we can speak about eventually. So this diamond says there is a point in the future where something happens, where phi is true. Okay, so it's like what I said after the customer paid, eventually they will receive the package. Okay, at some point in the future. I don't know exactly when, but they will receive it. And then there is the box that says always in the future. It means in every point in time from now on, something happens. Like once that the customer closed the order remains closed forever until the process finishes. Okay? So this is or if the customer already paid, the package has been paid in every point in the future. Okay? So it remains paid. We don't lose this information. Okay, so now just to continue with this. So what happens in practice is that we have this big graph that was the declared specification, as I mentioned before. But in the background, as I mentioned, this is just a huge formula on this language, on LTLF. Okay, so we just have this big formula that is describing the whole process, business process that we are modeling at the moment. Okay, now since we are in logic, since we are dealing with a big LTLF formula, we are able to do everything that we can do with logic, right? So using just the standard techniques from logical formalisms. Okay, so we can check things like satisfiability, right? So I ask somebody to describe me their business process, and I want to make sure that this business process is not contradictory, right? So that it doesn't ask things that cannot coexist, right? So this is in logic, this is the question of satisfiability. Is it possible that this is a process, a real process that can, that will have some traces running on? Now, we can also ask things like entailment. Like logical entailment means, given the constraints of my specification, am I sure that something else will be true? So every time that I satisfy my constraints, I'm satisfying another formula, okay? And so in terms of business processes means that I have a property that is guaranteed, okay? So is this something that I know that will always happen? Right? So like once that they paid, I'm guaranteed that the order will be delivered to the customer. And another thing that we can check that is kind of dual of entailment is safety. Okay, so is a situation that I want to avoid. Okay, so an unwanted consequence, right? An unwanted situation. Am I sure that it will always be avoided, right? So it's a kind of guarantee, but a guarantee of avoiding something that becomes impossible to happen. Okay, so these are the kinds of properties that we can check. And everything that that we're dealing with, it starts from here, from this declare specification. Okay, so but this is a nice theoretical language behind it. So when we speak about business processes, we can speak about declare, LTLF. We have this very nice specification language, and we can solve all these problems that I mentioned, reasoning problems. Okay, but in reality, what happens is that life doesn't like us as logicians, right? So life is not as nice to us as we would expect it, and the business processes do not run as we expect them, right? So there are two big questions. Well, the first one is, well, how do we construct the specification? Okay, so that's the first thing. So I mentioned in a real business process, we will have thousands of constraints. Do we really want a person, an expert, to go and describe all these constraints by hand? Of course, we don't want to, okay? Especially if it's a business that already exists, right? That has been running for years. They don't have their formal specification, but we need to build them. I didn't say this before, but so some businesses now have to build these specifications, even if they didn't want to, because there are some European regulations that are requiring some specifications of business processes to be published and followed and be traced. So that's also important. Now, the other thing is that, of course, I could have an expert that says, okay, this is my specification, and writes it in a nice graph, but let's say we have the agency that has to verify that the business is really complying with what they claim that they do. Okay, so how can we check that the process really complied with the specification? Okay, and so the answer for these two questions, although they seem like dual questions, the answer is the same, and it is that we can go and look at how the process has run so far. So this is, we look at the logs, execution logs of our business processes. Okay, so we have our online store. Every time that somebody connects and starts adding things to their basket and pays, etc., I keep trace of all these steps that they do, and this is one log, right? And so every customer does this every time that they order. So I have thousands and thousands of execution logs, and then I can extract. The idea is that we can extract this, the specification out of these logs, and I can also verify, looking at new logs, whether the specification is being complied with on the new executions. Okay. Now the problem, as I mentioned, so I was jumping ahead a bit before, is that in the real life, okay, these kind of deterministic specifications are not very good, right? Because in the real world, we will deviate very often from these specifications for different kinds of reasons, right? So some are under our control and some are not under our control, right? So for example, suppose that we have this specification that says, well, I should only ship an order after it has been paid, right? But if we have an active business, maybe we have some very good customers, our VIP customers, that they can order on credit, like saying, I urgently right now need this thing delivered, I will pay tomorrow, right? Since these are customers that always are buying with us, maybe we can allow this for them. Okay, so this will be a deviation of the specification, but by design, right? But we only want to do it for very specific customers, not for everyone. Yeah, just some exceptional cases. This is one possible deviation. Another possible deviation is by uncertainty, like, well, if the customer has paid, then they should receive their order, right? Okay, I can guarantee that inside my system, okay, my business, they pay, I make the package and I give it to the shipping company, okay? But then I don't know if the shipping company will really deliver it, right? So it might be that there is something, right? So if they have to travel by sea, maybe the container falls into the sea and then we lost the package, it's never delivered, okay? Or some other things can happen, it can get lost in the process. So there is a deviation by uncertainty because there is some things that we cannot manage, they are out of our hands. But again, we want this to be very exceptional cases. So we want to choose the shipping company that is more reliable, etc. Another thing is that we can say things like, Well, a constraint that says, well, a customer can only return an order if it has been delivered to them before. Right? Now, this also seems very natural, but notice that sometimes the timestamps in the different steps might be out of place. Okay, so this is a deviation by execution. So this can happen, for example, you receive a package, you open it, you realize that it's broken, you immediately ask for a refund and to send it back. But in the meantime, the shipping company has not yet marked that they have delivered to you, right? So in the system, it looks like you are asking for a return before it was delivered. But in reality, you have already received it, right? So this is a deviation by execution. Okay, but as I mentioned, so we should allow for these deviations, but they should be quantified in the sense that we want to have them really to be exceptions, right? So it's not that we say, well, we throw everything out of the window. We don't ask anymore that every shipped order must have been paid. We still want to have this constraint, but we want to relax it a bit so that we allow for these exceptional cases, right? So instead of saying every shipped order must be paid, we want to say something like at least 99% of the shipped orders must have been paid before. Okay, so this is a way of weakening these constraints. And this is where uncertainty and probabilities start to take into place. Okay, so this is where all this, after this big preamble, this is where these probabilities come into place with this temporal specification that we are dealing with. Okay, so we want to be able to provide guarantees, so reasoning, under uncertainty, under a limited amount of deviations of the design. Okay, so this is our goal. Okay, so just to put it into black on white, right? So the goal, our goal when we were dealing with this kind of language was to extend declare, or specifically extend the logical formalism behind declare, so LTLF, to handle probabilities. Okay, so now we want to say, okay, not my specification is not precise, is not perfect. We will have some deviation, some uncertainty on what is going on. Okay, but we want to still be able to measure, manipulate, and deal with these probabilities. Okay, with these deviations, we don't want to just throw everything away. Okay, now since our motivation still comes from this business process modeling in general, and with declare, what we want is to still have a language, so a probabilistic extension of declare or a probabilistic extension of LTLF that is clear, okay, and simple. Okay, so this is still part of our desiderata for the language that we are trying to build. We will see that we sort of take some liberties with respect to this desiderata, but this is the main goal. And this is the most important part of our restrictions when building the language, is that reasoning should be probabilistically sound. Okay, what does this mean? It means that if we are interpreting our relaxation of the strict constraints as probabilities, the results should really resemble probabilities. Okay, so this forced us to move away from some of the usual techniques that just assume that everything that we write is probabilistically independent, and then we just multiply probabilistic values. Okay, we realize that we cannot do this. We will see some examples, and so we have to really take the probabilities into account. Then afterwards, as we will see, we anyway have to approximate some details, so we don't have a full probabilistic specification, but we want to get as close as possible to that and know when we are getting away from. Okay, so what is the idea? So that's when we enter with this new language that we call PLTLF. We were very original in the name, so the P comes for probabilistic, right? So it's a probabilistic extension of LTLF. Okay, so it looks like LTLF, of course. So remember, we have all propositional logic, we have the next operator, and we have the until. So far it's just LTLF. but we added a new probabilistic constructor. So a constructor that allows us to say something about the probability of observing some behavior, okay? The probability of a specific formula, okay? So you see, this looks like a next. So we have a circle. So we put these two circles just to distinguish it from the usual next. And then we have an inequality operator. So it could be less than, equal, greater or equal, smaller or equal, etc. And a p that is a value between 0 and 1. So we are saying the probability of this formula phi in the next point in time should be, let's say, at least 0.8. Okay, so that's the basic idea. Again, we will see some examples in a second. Okay, now this is important. So I will not go into the full details of why. So there is a technical reason for this, but the probabilities are never local. So my formulas never say right now the probability of say paying an order is at least 0.7. What I can say is at the next point in time, the probability of paying the order will be at least 0.7. Okay? So probabilities always speak about the future. Okay? In the future, I will observe this. Okay? So that's the main difference, because keeping probabilities local in a temporal logic makes a big mess. Okay? So that's the main reason. Okay, so let's see some examples of what this works, right? So what this formula is saying, so let's just read it syntactically. What it's saying is, in the next point in time, x, so this is just a propositional variable, right? So whatever the x can be representative for, we will pay the order, for example, okay? The probability of paying the order, so the probability of x will be at least 0.9, okay? So what we are saying is, I don't know how I will evolve, okay? But it is much more likely that in the future, so exactly in the next point in time, x will be true than it will be that it is false. Okay, so that's the basic idea. Okay, so the probability of seeing x in the next point in time is at least 0.9, right? So now notice here the at least, right? So it could be 1, it could be 0.95. We're just saying it's at least 0.9. Okay, so this, I guess it fits a bit into the imprecise probabilities as well of what we are saying, because we are not saying a specific number. Okay, now we can make this as complex as we want, right? So notice this one, it's saying the probability that from the next point in time on, I eventually see x is at least 0.95. Okay, it's at least 95%. Okay, so what it's saying is I don't need to see x in the next point in time, right? So this diamond means eventually. So there will be a point in the future that I observe x, okay? And it is very, very likely that this happens. Like there will be a point in the future where the order will be delivered to the customer, okay? So this is what this is saying. The probability of eventually seeing x is at least 0.95. Right? So here we don't have to see it in the next point in time, we have to see it at some point in the future. Okay? Now, again, we can do complex, very complicated expressions. We can also put the probabilities inside other constructors, right? So we don't say that the probabilities are always outside the logical construction. So what this says is, in every point in time, okay, so the box means in every point in time in the future, always in the future, the probability of observing x will be at most 0.01. Okay, so we are saying always, so we can evolve, we can have a trace that is as long as we want. But in every point in time, it will be very unlikely to see x, right? So if x, for example, means that the order was lost, okay? So it is very unlikely that the order gets lost at any point in time in the future, okay? That's the point, okay? The probability of x is at most 0.01, right? Very unlikely. And again, we can make very, very complex connections. Okay, so these are just some examples to showcase the syntax and semantics. So here we are saying, okay, in the next point in time, x has probability at least 0.5. And also at the next point in time, not y has probability at most 0.9. Okay, so I have an upper bound for not seeing y and a lower bound for seeing x. Okay, so now, so this is the syntax. Now, if we have a language, syntax is not enough. We need to have semantics, right? So what does these things mean, all these expressions? So I said it in words, but in reality, formally, what does it mean? How can we manipulate it to get guarantees out of it? Okay, and this is where this name of the superposition semantics comes into place. So this is sort of a very free, so we stole it freely from the physics community. It's not really what in physics is superposition, but it's close enough so that we can give the name. So the idea is that we are observing a trace. Okay, so in the real world, when we are running a process, we are just seeing at each point in time what is happening. Okay, and intuitively, all the possible futures are there. Okay, so all the future configurations could happen, okay, until we observe each of the points, right? So right now, I'm in certain position. I don't know if in the next point in time, x will be true or x will be false, okay? So simultaneously, we can believe that they are both true and false until the next point in time comes into place. And then at that point, we observe x, then we know that it became x and it didn't become not x. And so that observation removes part of the possibilities, and then we go on. Okay? So the idea is that then as time evolves, of course, the same trace can fall into different superimposed states depending on what has happened in the past, right? Because remember that our specifications say things that can happen depending on what we have seen, right? So if now I have observed that it was paid, for example, the order, then the superimposed states change into whether the shipment can be lost or will it be delivered, or we miss something in the package or something will be broken. And those are the superimposed states that we are dealing with. And they can be changing as the trace evolves because we are observing more details. Okay? And now the point is, of course, this is a nice intuition, but how do we formalize it to be able to reason with it? And so we use a notion of interpretation, of temporal interpretation, that deals with all these superpositions, okay? And how does it deal with it? Well, remember that we say the future are the parts that we have not observed. And so in the future, many of these situations can happen. So in reality, what we are seeing is we are observing a branching of time, okay? But it's not that we believe that time branches, but the possibilities of what will happen are the branches that it can happen, okay? So let's get to this branching that I mentioned by starting from the LTL version, because I didn't mention what was the semantics of LTLF. I just gave it in general, okay? So in LTLF, so the version without probabilities, okay, an interpretation is just a sequence of propositional valuations, right? So we have our time. Time is discrete in LTL. So we have one point in time, then the next point in time, then the next point in time. And at each point in time, we say which things are true, right? So right now, X is true. In the second point in time, X is false. And in the third point in time, X is true, for example, okay? So at each point in time, we say which propositional variables are true or not. And it's just a sequence, a big line of propositional valuations, okay? One after the other, and then it stops at some point, okay? And so whether a formula is satisfied or not at a specific point in time depends only on the future points, because remember that our formulas only speak about the future, right? So or the present, the propositional descriptions, and then the future with the next operator and with the until operator. So each point in time only looks towards the future. Okay, so here is, for example, a very simple example of an interpretation in LTL. So the formula eventually X, okay, is true in this interpretation, right? Because so at the first point in time, X is not true, but in the second point in time, X is true. So we have satisfied eventually X. And then there are some other things that happen, but we have already satisfied eventually X, right? Another example, so we could have that, so we have x is false at the first point in time, false at the second, false at the third, then we observe y, but still not x, and then it goes ahead for a long time, and then after 1,000 steps, time points, we observe x, and so at that point, we have observed x, so at the beginning, eventually x is true, because from this point, somewhere in the future, I will observe x. Okay, now if we have this interpretation where x is false in all these points, then of course eventually x is false in this interpretation. It's not this interpretation does not satisfy this eventually x. Okay, I hope this is relatively clear. And for those of you that know LTL, this should be trivial. Okay, so now we want to lift up this semantics to this PLTL. Okay, so to the probabilistic version. Okay, now let's analyze the only operator that we have that is different from LTL. So now we have this probabilistic thing that says, well, it will tell us something about the probability of phi in the next point in time, right? Now, the thing is, we have to be careful because it also tells us something about the probability of not seeing phi, right? So remember the example, if I say something like, in the next point in time, the probability of observing x is at most 0.5. Well, it's also telling me that the probability of observing not x is at least 0.5, right? Because so I can, it's impossible that I always see x, right? So I have to have also the version where I don't see x. So I have to check these possibilities, both of them. Okay, so this is what I mentioned now in written. So if I say that in the next point in time, x is true with probability at least 0.9, well, this is also telling me that x will be false in the next point in time with probability at most 0.1. Okay, now again, it could be that I make x true with probability 1, and so not x becomes with probability 0. Okay, but it could also be that I put 0.9 and 0.1 to compensate. Okay, so that's the basic idea. And so in order to define the semantics of this logic, we have to consider both possibilities, right? So the case where x becomes true in the future and the case where x doesn't become true in the future, because both are there latent in the situation that I am in until I observe the next point in time, right? So this idea of the superposition semantics, okay? And so what we're going to do is, well, we are going to extend this notion of interpretation, as I mentioned before, to branch into to explore the different situations that we have. Okay, so let's look at an example. Okay, so this example for where we say, well, in the next point in time, the probability of observing x is at least 0.9. Well, what we're saying is that, well, we have this possibility that in the next point in time, I see x. Okay, but I should also take into account the possibility where in the next point in time, I do not see x or I see not x, right? And the point is that I should assign a probability to them, okay, that is coherent with this, right? So I could say that this is 0.9 and 0.1, okay, but I can assign any other probability in this branching as long as it is coherent with this constraint that I'm putting here, right? So it's saying at least 0.9, so this can be 1 and this can be 0, okay? And then, of course, it doesn't mean that the branches have to stop here, that the traces stop here. They can go forward into the future. Let's do another example, the one that says eventually in the future we see x, right? So it says that with probability 0.9, I will have a branch that somewhere during this trace, I would see x. Doesn't have to be at the first point in time, right? But somewhere I will observe x because we are saying eventually x. Okay, but with probability at most 0.1, I have to see the other branch. In the other branch, I should make eventually x false. So everything, every point in time in the future should have not x, because if I put x, it will be the case that is satisfying eventually x. Okay, so you start seeing that now that's where probabilities and the temporal variant start playing into tricky games, because once that I'm here, I'm saying I must always have not x, right? So here in this branch, I must have eventually x, and in the other branch, I must satisfy that I never see x at all. Okay. Now I mentioned, you start seeing so that the logical part starts messing with our probability. So that's why we cannot assume independence, right? So this is the main point. So what happens if I put a formula inside of one of these constructions that is always true in every possible temporal interpretation, if in every possible trace? Okay, so suppose that phi must be true. And then I say that with probability at least 0.9 phi has to be true. Well, it's saying, so if I follow these semantics, it is telling me that I will have a branch where I make phi true, and I will have another branch where I make phi false, right? But what is the issue? Well, that phi can never be false. So this branch here cannot exist, okay? So logically, I cannot produce this branch because now, so this is sort of like having a superposition that violates the laws of physics. Well, that other superposition case is impossible, so it's not really superimposed. We only have one state in our value. So that branch over there is impossible, and so we have to assign necessarily, so here is not a choice, but this is a necessity, the branch where phi is true, the probability 1, and the other branch is not only that I assign probability 0, I just cannot create it. It doesn't exist because it is asking me to satisfy something that is impossible to satisfy. Okay. Why is this important? Because, well, in this example, it's trivial. We say probability 1. But what if our probability bound was smaller equal? Then the smaller equal is forcing me to have the branch where phi has to be false, right? But that's impossible, right? So I cannot assign a probability to this into these branches. And what I get is, in the end, a formula that is unsatisfiable. Okay, so this is a formula that is inconsistent by itself. I cannot satisfy it in any model. Okay, so I hope this is clear. I will start going faster because I realize that I'm going a bit slow. But so what happens if we have more than one probabilistic formula together, right? So like here, I have a conjunction that says, well, the probability of seeing X is at least 0.9 and of seeing Y is at least 0.9. Okay, so suddenly in our superposition, we don't have two possible states, but we have four, right? So whether both X and Y are true, whether X is true and Y is false, X is false and Y is true, and both X and Y are false. Okay, so we start getting four branches, the ones that I mentioned. Okay, now, of course, these branches have to satisfy these probabilities, right? So what it's telling me is that the first constraint, the X has probability at least 0.9. It means that these two branches together have to add to a probability of at least 0.9. Okay. The second constraint here is telling me that the first branch and the third branch, the ones where Y is true, have to add to probability at least 0.9. Okay, and then the other ones have to do accordingly, right? So one possible model would be like this, right? So which would be if we have sort of the independence assumption, right? So to this branch, I give probability 0.81, then to these two branches 0.01, and to this branch 0.01. But of course, there are other possible models that we can do, but we have to check all of them. Okay? And as always, also as before in the previous slide, the big question is, are these probabilities always feasible? That is what we have to do. Okay. Now, returning to what I mentioned about independence assumptions. Okay, these probabilistic constraints can have complex logical dependencies where we cannot always just assume independence of the probabilistic values. Okay, so consider this case where I say, well, the probability of observing X is at least 0.9, but the probability of observing X and Y is at least 0.8. Okay, now we can do the branching as we did before, but let's look at this third branch over here. Okay, so I put it in red here. So this third branch is telling me X and Y are true at this point in time, but X has to be false. Okay, so of course that situation again is one of those where we would be violating the laws of physics in this metaphor, and so it's an impossible superposition. So this branch, the third branch, doesn't exist. Okay, So we now have to distribute the probabilities over these three other branches. Okay, this one has a probability 0 and cannot exist again. Okay, so that's what makes this language complex to handle. Okay, in general, what we have is that our interpretations, the interpretations with which we define the semantics of PL/PLF, are tree-shaped. But as you notice, so this is, of course, an abstract example, not all the branches have the same number of children, not all the nodes, right? So here we have only one successor, here we have 3 children, this one has 2 children, etc., because we might encounter situations where we don't want to create one of the branches, or we cannot create one of the branches, like in this case, right? So this one, although it formally defines 4 possibilities, a model can only put 3 possibilities in the branching, because this one, we can never produce it. Okay? And so the tree-shaped interpretations are trees where each node is labeled with a propositional valuation. So you see it's the extension of the LTL semantics, where remember every node was labeled with a propositional valuation. But now instead of having a line, we have a tree that is again describing the possible evolutions that can happen in the form. And we assign a probability value, a number between 0 and 1, to each of the edges here. Okay? And well, with the constraint that they have to add 1, because otherwise it's not a probability, but that's a different thing. Okay? Now, the point is that each of these branches represents a type of trace, right? So it represents the behavior that we will observe. It might not be enough to know exactly the full behavior, but if I have here that says eventually I will observe X, well, here at some point I have to see X, but it could be in the first point, in the second point, in the third, etc. Right? So it doesn't matter for the type that I'm trying to represent, that where the shipment was delivered, for example. Okay. Now, as I mentioned, we cannot require all the branches to exist. Okay. So how do we actually manage to deal with this problem? Okay. Well, in logic, we sort of take some shortcuts, and we can just assume that we have an oracle that allows us to know which are the good branches and which are not. Okay, so we can say, well, we can non-deterministically guess the number of branches, which are the ones that can be satisfied together. Okay, so there is an oracle. Of course, the oracle will be a logical reasoner, but we can just assume that this is there, non-deterministically guessing. And then we try to solve the numerical constraints. Okay, so the branches have to add to 1, but they have to satisfy the constraints on the next probability in the next point in time operator. So they have to add to at least 0.9 or to at most 0.5, etc. And we have to check that locally the logical parts do not contradict each other. Okay, so this I'm saying fast because it's just the technicalities of how it works. I'm just hand waving a bit. But the idea is that for the numerical constraints, we have a system of inequalities, okay? And then we have to deal with a bit of recursion to deal with these logical constraints, okay? And then we just have to check whether this system of inequalities together with this recursive procedure has a solution. If it has a solution, any solution that we build is a model. And so the formula, the specification that we created is satisfiable. Remember that once that we are in declare, we are trying to see whether the specification makes sense at least. Okay, so we have this specification. Okay, now as mentioned, I just described this process hand waving. So the actual algorithm is very technical. We can discuss it if you want, but I just wanted to give you the basic intuition, which I hope it is clear how it works in general. Okay, so once that you understand this intuition, which I hope, I know that is a bit fast, but I hope that this is relatively clear. Why is it useful? Because then if we want to check whether a specification is satisfiable, we can just use a tree automaton to do this. Why? Because you see what we did is we are trying to construct a tree that has certain properties. Okay, and how do we write a tree? Well, we can write a tree or label a tree just following the execution of a tree automaton. A tree automaton is a machine that starts with the node with the root node of the tree, and then moves downwards and starts trying to label it with different states. And we just have to check that these constraints that we have mentioned are satisfied. Okay, so to build the transitions, we have to solve these systems of inequalities that I mentioned hand waving before, but this we can do before. So we do it once, it's a long process, but now that we have it, we know which transitions are possible. And then we can just run the standard emptiness test for an automaton that is very fast. There are several implementations for this. Okay, so again, I'm saying it a bit fast, but because I want to get to these results here, right? So the main point is, well, you notice that if we have 2 constraints, we have 4 possible branches. If we have 3 constraints, we have 8 possible branches, etc. So this grows, the branching factors grows exponentially. So the automaton that we will build will be very big, okay? But we know that emptiness test of a tree automaton is polynomial on the size of the automaton, okay? So even though we have to build an automaton that has exponential size, okay, we can check satisfiability of a PLTLF formula in exponential space, okay? Now, to get this, we have to use non-determinism, etc. Again, this is hand waving, but so it's not as bad as one can expect. So we can check it in a reasonable time. So it's already exponential, but among the reasonable exponents that we can have. Okay, but the point is, well, yes, I do. So I add a lot of probabilities. I say something, but then in the end, I just want to check satisfiability. This doesn't make sense, right? So because why do I have the probabilities? Okay, so in reality, what we want to do is we want to reason about these probabilities, right? That was our original goal. Okay, so the things that we might want to get is how likely it is to see that something happens, right? So to see one behavior. Or as we mentioned, is the business process safe? So am I sure that I will not be shipping things for free to users? Okay, so am I guaranteed that I will not lose money with these exceptions that are there? Okay, or more interestingly, perhaps, is what is the usual behavior of my business process, right? So what is the most likely thing that I will observe? If I start running my process now, what is what I expect to see, right? And so the question is, well, and in those cases, what is the probability, right? So what is the most likely trace and what is its probability? How likely it is that I see? Because it could be that the most likely trace is something that has anyway a very low probability because we have lots of different possibilities that can happen. Okay, and so now here perhaps is this imprecise probabilities view more clear. We have this approach where we have an optimistic and a pessimistic view. Okay, so now just to give you the idea of the optimistic view, the pessimistic view is the dual. Okay, so instead of maximizing, we will be minimizing. But so our 3 models, again, are just describing this superposition semantics. So we have a way to describe in a compact way lots and lots of possible linear interpretations, right? So we are just collapsing them into a tree so that we can observe them easily, okay? But we have many different interpretations that are just compacted into one, okay? So each branch in the tree model that we have built is in reality one possible execution of our process, okay? That's the whole point. Okay, so we have the branch where X doesn't happen is because it's a possibility in our execution in our model. Okay, so just what is the most likely trace? Well, the most likely trace would be those branches or one branch that maximizes the probability over all the possible models that I can find. Okay, now I said here the most likely trace, but in reality is a most likely trace because we can have lots of different traces that have the same probability, this maximal probability that it has, okay? So this notion of most likely trace can be extended to the most likely language, okay? Give me the language of all the traces that are the most likely to be seen. They have the maximum probability, again, optimistically, okay? So if I use the model that has the biggest value for that branch possible, okay? Now, very fast, because I'm running out of time, how do we check for this most likely language? Okay, Well, in reality, the technique is very simple. Once that we have built our tree automaton, okay, the tree automaton tells me at each point in time, what are the branches that I can, so what are the possible successors? Well, instead of doing that, I just construct one successor at a time. So I flatten the tree automaton into a string automaton, but not a normal string automaton, but a weighted string automaton, where I assign to each trace, to each transition, the weight as the maximal probability that I can assign to that branch. Okay? And so the behavior of this automaton, so given a trace, what is the probability that I get at the end, the value, the weight that I get at the end, is the likelihood of the most likely trace. So the probability of this most likely trace. So I get the value, a number. For each trace, for each word, I get the probability that it gets, and the maximum of this would be the probability of the most likely trace. Okay? Now, if I get the weights, if I get rid of the weights, but only keep the transitions that have the maximal possible weight at every time, I can find the most likely language. Okay? So again, I'm saying this very fast, but is once that we build the first automaton, the tree automaton, then we just simplify things, and then we solve other problems and other reasoning problems in this language. Okay, and very nicely this gets down to p space. Okay, so from x space, exponential space, to polynomial space, so after a very big pre-processing. Okay, let me just, I don't want to say this. Let me say one last thing about a variant of PLTL that we call PLTL 0. Okay, so because you notice the language itself is very complicated. Okay, so what we realize is that with our motivation of declare and business processes, in reality, what we are describing when we do a business specification, we don't say things that the probabilities that will happen after some actions take place, but our constraints usually just say something about the beginning, right? So at the beginning of the process, I tell you things that will happen, okay? So also all our probabilistic constraints that are relevant refer of things that we observe at the very beginning. Okay, so this motivated a restricted version of PLTL, of PLTLF, that we call PLTLF0, okay, that says, okay, we only have probabilistic constraints that are at the topmost constructor of the logic, okay, so they belong at the beginning of the trace, okay? So we have uncertainty about which will be the branch that we take, which is the possibility. But once that we decide which is the branch that we are taking, everything is linear. So we will have a linear execution. Later on, we don't have any probabilities to deal with anymore. Okay? So we only branch at the very beginning. So we have a root that branches at the very beginning. That's the multiple word semantics. And then we just have lots of linear executions. So just linear temporal logic in the classical sense. Okay. Okay. So that's with this PLTLF0, we reduce a lot the complexity of describing constraints, specifications, but also of reasoning with this logic. So we get back to P space, which is the usual reasoning complexity for LTLF. So we cannot do better than that anyway. Okay. Yes. Okay. So I just want to say something about the future, okay, of this, because I think it's important. Well, you remember one of the questions that I said at the beginning, where do these specifications come from? And they say, well, we can read them from the logs. And usually the question is, where do the probabilities come from, right? So where do you get the probabilities? And we can say, well, we can get it from the logs, right? So I have a log, and I see that in 90% of the cases, an order was shipped after it was paid, okay? So we can say, okay, with 99% probability, we ship after it was paid, right? Now, the thing with this, and so this is what I want to say about the future, is that the logs are not complete information about all the possible traces that we can observe. but they are only a sample of our population. So we have an infinite population of all possible traces. We cannot observe this. We can only see a sample. Okay, and so when we are using a sample, in our case, if we say we use this as this information in the log to get the probabilities, what we are doing is that we are using most likely estimators for our probability. Okay, but in statistical terms, so not in probabilistic terms specifically, but in statistical terms, most likely estimators are not fully informative. Okay, about the population. We can get more information if we use statistical methods for sampling. Okay, and so this is the thing where I will just leave it as work for the future, is that there is a need, if we want to do this in a sound way, in a sound probabilistic way, to not just use these most likely estimators, but have really a statistical temporal logic where we have probability distributions, right? So it's not enough to say the probability of observing this is between 0.7 and 0.9, but we have a probability distribution that we can say, well, it's a normal with mean at 0.8 and standard deviation something, and then we can get more information about it. And with that information, then we can know about quantiles, right? So outliers, exceptional situations, different cases. And with that, we can do forecasting and better predictions that we cannot do formally or in a precise way in our language. Okay, and I think I got exactly 1 hour, maybe a bit more. Sorry if I took longer, and but I'm finished. Yes. And
okay.